Thanks for coming, everyone, and thanks to Unbalanced for hosting. So how many people, who, for them, this is the first time they've been to one of these meetups? Raise your hand. Okay, keep your hands up. How many people have a research background? Keep your hands up. Okay, how many people have a programming or software engineering or whatever background? Okay, keep your hands up. How many of you are experts at machine learning? Okay, so I'll explain just an analogy, just so the talk makes more sense. So think like, you hear machine learning AI is this magic that does stuff, right? But think of it like this. Okay, you have a function or a procedure, right? Like when you're programming normally. And what machine learning does is it basically fills in the code on the inside. And the way it does that is you get a bunch of examples of what you want. Like, when I get this input, I want this output. When I get this input, I get this output. And it magically does that. Now, some of that magic, Mark's going to talk about. So actually, before we get to that, I had notes. Give me a sec. So the first thing I'll say is there's other events related to this. Like, for example, there's a Kaggle competition stuff that they do, and we also do a reading group. So Bruce is going to tell you about the Kaggle competitions. Bruce?
Hi, folks. How many people here even know what a Kaggle competition is? Almost everybody. Cool. So what you may not know is that there is a meetup group that meets every 2 weeks, and the name of this meetup group is Learn Data Science by Doing Kaggle Competitions. So those of you who don't know what a Kaggle competition is, they're these online competitions that are posted by real companies, usually people who actually have some data, and they post a machine learning project, and it's open to everybody to participate. They're really great for learning how to do machine learning data science, because everyone's very, even though there's cash prizes for the winners, everyone's very sharing of their code and knowledge and so on. So what we do in the meetup is we pick a past competition that's closed, and we do that because it sort of avoids running into problems with the live competitions where there's a lot of rules you have to follow. But it's still good because all the data is still available. You can still run your train things and test it and see how well it does. And people have posted their solutions, so it's a great way to learn quickly. So every 2 weeks we pick a different competition. Somebody sort of volunteers to read about it and then walk the rest of the group through it. So someone's looked at it in detail, but everyone kind of looks at it, and we have a great discussion. Great way to learn. So look for us on the on Meetup under Learn Data Science. Google for Kaggle Learn Data Science on Meetup, and you'll find us there. And I hope you can join us.
Dave Campbell's going to tell you about the reading group.
Hey folks, I feel like I need to do a survey, so how many of you know how to read? Great, there's a reading group that happens every other Wednesday. It happens out of Harbor Center, SFU Venture Labs. We host it out there. Everybody can suggest a paper, we vote on them, and then what happens at the reading group is we talk about the papers. Now, some weeks it's something that you know a lot about and you're coming with your own expertise to help everybody out with, and sometimes you maybe don't really know what's going on in that paper, and this is a great time to fill in some holes and to ask some questions. And it's a very open community in there, and we tend to read a big variety of things. This coming next Wednesday, a week from Wednesday, we're going to be reading about election polling and how that works. In other times, we've done things on machine learning algorithms or Bayesian modeling, and just a big mix of stuff. Thanks.
Thanks. You ready? Mark? Yeah, cool. So Mark Schmidt, he knows a bit about machine learning, I'd say. So he's going to be giving a talk on that, how you deal with it when you deal with big data. So that creates problems. Mark?
Thank you. All right, so thanks for the organizers for organizing. Thanks for everybody for coming out. I'm sorry for the people who were standing, and for the people who came here and waited for a long time. I'm not going over the title in the meetup group. I'm doing this title instead. If you Google this, it's exactly the same way of saying the same thing, but it's a bit more technical. I've given this talk in a lot of places. So the talk is about a paper from 2012 that sort of changed the way we look at machine learning and a lot how we train models. So I've given this talk kind of all over Europe, all over North America. Been to Asia a few times, Australia. I went to Brazil in May this is going to be like, but they said that the current version of my talk had maybe too many equations. So we've tried to make this a bit more accessible to everybody. Oh, I'm that guy who drops the mic. Okay, if I drop the mic again, I need the people at the back to start waving your hands, especially if you're standing. Okay. So I just recently snuck in some slides after hearing the results of that survey. So we're going to do a little bit of an intro to machine learning before we start on the more technical stuff. Okay, so why is machine learning so important right now? It's this big data phenomenon. We're using technology to collect and store data at an absolutely unprecedented rate. If you think of all the data that's being stored around you, we've got things like news articles, so we've got hours of video uploaded to YouTube every second, credit cards transactions, we're mapping the human genome, mapping the sky. The Large Hadron Collider has 1 trillion experiments. Phone calls are being recorded like crazy. We're recording every single click you do on Minecraft or Pokemon Go. Why not? So people call this big data. It's kind of a buzzword, but we really are collecting tons and tons of data. This is where machine learning comes in. So we want to use this data for fun, for profit, or for the greater good. But there's just way too much data to search through it manually. There's traditional ways we think of using data, put it in a database, look at tables, things like that. They just don't work when you're looking at data that's so big you can't even look at it. Are we okay at the back on volume? Great. Okay, so machine learning is one of the ways we deal with this huge amounts of data. The idea is we want to use computers to automatically detect patterns in data and to use those patterns to help make predictions or decisions. It is very similar to statistics, but there's a bit more emphasis on large data sets and computationally feasible methods, a bit more emphasis on doing predictions instead of just descriptions, and more emphasis on flexible models that work on many problems rather than thinking very hard about one model for one problem. So the typical machine learning framework, which was just mentioned, is supervised learning. So as an example, I want to build a program that's going to distinguish cats from dogs. So the way I do that in the machine learning approach is I collect a whole bunch of images of dogs, and I collect a whole bunch of images of cats. Now I'm going to use that data to learn a model that maps from the inputs to the outputs. So the output of that is going to be a program or a model where if I give it a new image right here and I give it to this program, it's going to spit out cat, even if it's an image it's never seen before. So if people just want to ask questions or whatever, just raise your hand and we can talk about other things. I'm hoping that most people have seen this before, but if you haven't, you can imagine that you can do this for many different tasks. I really don't care about recognizing cat versus dog images. I think most people probably don't. But you can imagine this could be any input and any output, and you can maybe think of something that's more useful to put in there. So now one way to think about this is the input is data and the output is a program. So this is a little bit different than the usual way we write a program where we have input specifications, output specifications. Here we have examples of input and output, and we have lots of data, and we're going to use the data to write the program for us. Typical cases where this is useful: the problem is too complicated, so we can't write the program ourselves, or maybe we have a human expert and they can't explain why you have a certain input or output. Or you just don't have a human expert, but you have labels somehow and you want to hope for the best. This is a very fast-growing field, as evidenced by over 200 people in this room right now. There's been large investments from Google, Facebook, and Elon Musk. Lots of local companies applying these ideas. And in academia, the top machine learning conference, NIPS, increased from 2,500 to 4,000 last year. And I don't know what it's going to be this December. It might be less because it's in Barcelona and lots of people have visa trouble, especially because there's no Spanish embassy on like this side of Toronto. You do if you are from Iran or India or where many of my students are from. Okay. So I shouldn't need to convince you of this, but machine learning is now affecting our daily lives. If Gmail is putting something in your spam filter, that's a system that was built with supervised learning. There's lots of websites that do product recommendations. If you play on your Xbox and you're playing Microsoft Connect and you're moving it around and it knows where your limbs are, that's a system called the random forest. Optical character recognition is a classic problem in ML. Translation is now being taken over by machine learning methods. Speech recognition on every single smartphone is a supervised learning system. Face recognition is not always supervised learning, but almost always it's some sort of method you would see in a machine learning course. Sports analytics has got into things like non-negative matrix factorization. So they're using machine learning for sports now. I watched a talk by the guy who made this chart. He was a geographer, the guys who make maps at Harvard, and now he works for the San Antonio Spurs because he started making maps like this. Object recognition is coming. Pretty soon your phone is going to recognize your kids or where your remote control is. Self-driving cars are on the road and it's a little bit terrifying. Machine learning is used for scientific discovery. So this was a case where a machine learning visualization was used and they found there was new types of leukemia. And this is my old office mate. He wrote a program that's supposed to basically take money away from statistical consultants. You give it your regression data set, it'll write you a paper about the data set. This plot, the caption, the numbers, all that, it spits out a paper describing all the different trends in your data set. So you don't have to pay anyone, does hypothesis testings and all that stuff. He's faculty at U of T, just started in last month. Okay, so I just want to convince you that if you're not already sold on this, machine learning is doing some really cool things. It's not magic. If you have a problem you really want to solve and lots of data, that's not enough for machine learning to be ready to solve it. It really has to be in one of these nice formats like supervised learning. But if you can put your data in that format and you've got nice data, you can do some really amazing things. Okay, how are we? Good at the back? Yeah, everybody's happy? All right. Oh, and if you hate all this stuff and you just want to paint pictures, people are doing machine learning for that too. So here's a picture in Tübingen, which is one of the top ML centers in Europe. You give it your picture of Tübingen, you give it a Van Gogh, and it'll spit out a Van Gogh version of your picture. How cool is that? Yeah, I'm going to start putting these on my wall. Actually, Google started selling these for way more money than Google needs to sell paintings for. Okay, so that's sort of like, machine learning, why should you care type of thing for those people who are here for the first time and haven't seen something like this before. Now I'm going to get into the more technical part of my talk, is that most machine learning methods are written as some sort of numerical optimization problem. You want to minimize some cost function. And that cost function is going to tell you how well your program is at getting from the input to the output. So if the cost function is very high, you give it a picture of a cat and it says dog, or something like that. If the cost function is very low, it means you're doing well. And a classic example from stats and from numerical linear algebra and from machine learning is least squares. I want to minimize some function f of x. I make a prediction that's a linear combination of my features. Yi is my target, that's whether I'm cat or dog. And I square the difference and then I sum it up over all my training points. If you've never seen a linear model before, you probably should just listen to what I say as opposed to stare at the equation, but many of you have seen linear models before and you've probably seen this equation many, 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 many times. Okay. Great. Okay, but we're not even going to need that notation. I'm going to talk about an even simpler problem. I'm going to talk about, I want to minimize a function f of x that's the average of a set of individual functions fi of x, and we're going to assume that those fi's are differentiable. I can take the derivative. So it's a super simple problem. You would think that everything that would have been said about this problem would have been said in the 1800s, but it turns out we learned something kind of fascinating in 2012 about this problem. So you can think of this as measuring the average error f of our costs fi and individual examples I. So this fi of x, that's low if I've predicted image I as a cat and it actually is a cat. And it'll be high if that's not a cat. That little framework, this minimizing sum, basically includes almost all of machine learning. You've got logistic regression, SVMs, PCA, CRFs, deep learning, regularization, all that sort of stuff. So I haven't really made any restriction yet. I'm going to have to make one restriction to sort of make my life easier. I'm going to focus on something called convex optimization. Now, the convex functions are a class of functions such that if I go downhill, minimizing the cost function locally, I'll eventually find the global maximum. So whenever I find a local minimum of a convex function, it happens to be the global maximum. These are among the only efficiently solvable continuous problems we have. And you can do a lot with convex models. So a whole bunch of the machine learning methods we know and love are in fact convex models, so they're included. We have lost some more notable things like deep learning and PCA though. But the empirically effective non-convex methods tend to be based on methods with good properties for convex functions. And if you have a good method for non-convex functions, it better have good properties for convex functions, because near a minimizer, every function looks like a convex function. So if you don't have good properties for convex functions, you don't have a good method. Finally, tools from convex analysis are now being extended to the non-convex case. We've been working on non-convex optimization for decades and decades and decades. We finally have some nice methods with provably good properties. Many of those are coming from the convex world and going into the non-convex world. So the convex world has been very fruitful in the past few years. Okay, does anybody want to make a comment or throw up a question? Does anyone want to be brave at this point? Way at the back.
Just hang up the mic there. Is that 3 or 4?
How do you know, when you start with some data, how do you know that this function that you are fitting has convex property or not?
Okay, yeah, so how do you know if a function is convex? I covered that in my class today. There's a bunch of rules you can go through, and you can prove that your function is convex. The thing about the convexity is it's not a property of your data set. It's actually a property of the particular cost function fi that you pick. And then if you know, SVMs are always convex, no matter if I'm distinguishing cats versus dog, or spam versus not spam, or your lim and connect. So in some sense, you usually know beforehand whether your function is convex.
So yeah, sorry, I think it's better to ask this question then. So when you want to start, let's say, training a model, how do you know the model that you are picking is going to be the right model in order to reach to the optimal point, I guess? I don't know how to phrase the it's more kind of practical question I have. So when you want, let's say you have some data, and if you fit a model, how do you know that, you say that the model should have, if you know the model has a convex property or not, yeah? That was the thing that you said beforehand. But how do you know that kind of model is the right selection?
Okay, so that's a great question, and that's a question that has a very unsatisfying answer. So in machine learning, there's a theorem called the no free lunch theorem. And some people are like, yes, all right. Okay, so the no free lunch theorem says that if I look at data I've never seen before, if I'm truly looking at images of cats that have not been used during training, all models are equivalent in some sense, in that if model A works better than model B on one task, model B is going to work better on model A on another task. So the implication of this is you have to try stuff out. You have to figure out what works for your types of problems, which models work better. So there's no way to a priori say that one model works better than another one unless you've seen similar problems. So a lot of this actually comes from experience as opposed to theory.
Is this mic working? How does regularization fit into the convexity?
Okay, great question. So almost all the usual regularizations not only are convex, so things like L2 regularization, L1 regularization, so on, those are convex, but they actually, especially L2 regularization, makes your problem strongly convex. So if you look at my papers, that's sort of a crucial part of the theory. We've subsequently got rid of that, but actually regularization makes your function more convex. It makes it more nice, more easy to solve, just like it improves your test error. Okay. So, classic approach to convex optimization. It comes from like 1847 or something like that, so older than everyone in the room, is called gradient descent. And if you go to my webpage, I have that paper linked. It's in French. It's scanned by the French library. We do have a paper copy at UBC. The papers are completely yellow, but you can go and check it out at UBC too. And it's by a guy named Cauchy, who if you've taken math classes, you recognize the name Cauchy. He's a super famous real analysis guy. Okay, so gradient descent. For this particular case, we go through our entire data set to compute its gradient, and then we update our model based on its gradient. So we're going to start with some guess, and we call it x0. And now I'm going to generate, when I have x0, I'm going to generate x1, and then I generate x. Once I have x1, I generate x2, and so on. So I'm going to generate a sequence of guesses. Each one is going to be better, and the way I do that is I subtract a small step size times the gradient. And conceptually, we're thinking about, we have our function f of x. We're at some point, it has a slope, and we go in that direction to decrease the function. We take the gradient and go on, and then we hope we get to a minimizer. When we're in this setting of minimizing these huge sums, the gradient of the average just ends up being the average of the gradients. And that's just because derivatives are additive. Okay, as a picture, if we're imagining this is like some sort of bowl, and the minimum of the bowl is here, so we're coming out of the whiteboard. So think of this as like a temperature map, where like this is the hottest area, and then we're getting like colder and colder and colder as we go out. If we start here, we're going to move inside the circle, inside, 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 and you hope you eventually get to the minimum. Now, nice thing about this algorithm, you can prove the number of steps is polynomial. If you're a computer scientist, you're happy. Polynomial is what we want. This is good. Every step of this algorithm needs to go through the entire data set. I need to compute gradient on image 1, gradient on image 2, gradient on image 3, all the way up to gradient on image n. And today I want to talk about the case where the number of training examples is very, very large. So there are fancier methods that you may have learned about, like quasi-Newton methods and so on, but they're still going through the entire data set to compute a gradient. So they still have this problem. Okay, so if our data set is every web page on the internet, or every product on Amazon, or something like that, this is too slow, right? We're not going to go through the internet 50 times to try and find a minimizer. We're going to go through it 1 time, or 2 times, or 5 times. We have to update as we go. We can't just wait and compute these gradients. They're just too expensive. So if you've taken a machine learning course, they give you a standard answer. You use something called stochastic gradient. Instead of looking at every single training example, you look at one random training example in our data set and you compute the gradient of that one example. Then you update the model just based on that individual one. So we can imagine, instead of going through the entire internet to see how well our classification of this is, if this is a whatever you want to classify, you just look at one random web page. I take the gradient of that one random web page, gradient f of it of xt, and I do gradient descent as if that was the entire internet. And as you can imagine, that's kind of a crude approximation. Representing the entire internet with one web page, not great. But I'm going to do this over and over and over again, and on average, it's still going to point me in a good direction if I do this many, many times. So here's the same picture for stochastic gradient descent. So stochastic gradient descent is like gradient descent's like drunk cousin or something like that, where it's not always pointing straight down. It starts out taking big steps. It sometimes goes up, outside the circle, inside. Slowly the steps get smaller, and eventually you can converge. If any of you have played with this algorithm, this picture is being very generous to stochastic gradient descent. It does not work even close to this well. Okay, but here's the advantage. Every step only needs to look at one example. So if I have 1 billion data points, one step of this algorithm is 1 billion times faster. That's a speed up that's hard to ignore. There's not many times in computer science life where you get to make something 1 billion times faster. But that doesn't come for free. The number of steps is actually exponential. And if you're a computer scientist, that should make you uneasy. We don't want exponential time algorithms. It could take you until the end of time to get high accuracy. You might quickly get to 1 digit of accuracy, and to get that second digit of accuracy, you might need to multiply your runtime by 1,000. It's not cool. It's also a PITA, which stands for pain in the ass, to set the step size and to decide when to stop. Especially those of you who've been around for a long time and learned about neural networks in the 80s or 90s, you probably did some playing with this nonsense. It's really annoying. So we've got an algorithm that's slow, you don't know how to pick the step size, and you don't know when to stop it, even if you could pick the step size and even if it wasn't slow. People love this algorithm. Okay, so we've got a trade-off here. We can do a small number of very expensive steps, or we can do an enormous number of very cheap steps. And anyone who tells you one algorithm is better than the other is wrong. There's no strict dominance. It depends on what you want and what you have. So here's our deterministic algorithm. I go through my entire data set, computing gradients and doing nothing. Once I've got every single gradient, I take 1 step to improve my cost. I go through my entire data set again and take 1 step. Again, take 1 step. But the steps are actually making quite a bit of progress. The stochastic gradient method is different. It's taking a whole bunch of little tiny steps, and after it's gone through the data set 1 time, it's actually made a ton of progress. But the longer you run it, the less progress it makes. It starts to get flat. So, if you only have this much time, you should pick that stochastic gradient algorithm. If you have this much time, you should pick the deterministic algorithm. If you only need this level of accuracy, just run the stochastic gradient algorithm. You don't even have to go through your data set 1 time to get that accuracy. If you need this level of accuracy, and otherwise your self-driving car runs into white trucks or something like that, then you need the deterministic algorithm. You need that high accuracy. Okay, so everybody in this room probably knows where I'm going right now. We've got 2 algorithms. So one does well in one situation, one does well in another situation. Everyone can probably think of some algorithm that maybe tries to do in between. So maybe I'll run the green algorithm for a while and then switch to the blue one. Or I'll make an algorithm that's intermediate and starts looking like the green one and slowly turns into the blue one. You can do that. I'll talk about that later. But what I want to say is we're going to actually get an algorithm that's better than those strategies, that actually works, that gets the best of both worlds and cleans the clock of both of these algorithms. Okay, I just want to pause here to see if anyone wants to bring up any comments or anything like that at this point. Yeah?
That graph that you showed, that's in theory you can prove it, or that's kind of your empirical observation?
This is the theory. So this will be an upper bound on the progress of each algorithm. I'll show plots later in practice that look almost exactly the same.
Okay, and so in theory, in theory, you can prove that there is no any way that stochastic gradient descent error goes to 0, yeah?
The error does go to 0, but asymptotically.
So it's very slow.
Yeah.
Okay, thank you.
Yeah.
So why does the stochastic slow down?
Okay, so the issue is when you have a really bad guess, almost any of those random web pages or random training examples you pick is going to give you a good direction. As you start to get better, that one random web page is a worse approximation of the direction you need to go. As your model gets better, you need to have more information to keep making progress. And so really the key is you need the variance between your different gradients to go down to 0. And if that doesn't go down to 0, then what you need to do is you make the step size go to 0. And so stochastic gradient starts taking tiny, tiny steps to keep making progress.
There's also Mike on that side of the room if anyone is shy and feeling stuck over there.
I'm being completely blinded by that side of the room, so I can't really see what's happening over there. Okay, why don't I move on? And I'll try just, someone stand up and start jumping up and down if I'm the bad mic guy. Okay, I'm definitely not the first person to think about speeding up stochastic gradient methods. The first paper on this topic was from 1958. And that's, well, let's just talk about the things that have been out there. So there's, You can play with the step size. Momentum is very popular in the neural network. There's things like averaging and AdaGrad and Atom and RMS prop. And maybe you think, I don't want to do gradient descent, I want to do Newton's method, and I'll make a stochastic version of Newton's method, or something called Nesterov's method, which is more recent. I can prove to you that none of those methods are going to work. All of those still require an exponential number of iterations. The Newton one is really scary, because for deterministic methods, Newton's method is awesome. Newton's method gives you sublinear convergence, or superlinear, depending on what your community is. The 1958 paper tried to look at constant step size stochastic gradient, and then there's more recent papers. These give you a polynomial number of iterations to a fixed solution quality, and then after that, they stop making progress. So if you just use a fixed step size, you go down very quickly to some solution quality, and then you just start bouncing around. And you really have no idea what's going to happen there. It'll never really converge. If you're stuck using stochastic gradient, this is usually what I recommend people do. And then you can think of hybrid methods. So here you get a polynomial number of iterations, but usually you eventually start making full passes through the data. So you have something that's stochastic early on, but then becomes more deterministic as you go. And then finally, for some very special problems, we know that you can actually get faster algorithms. So if you have what's called a consistent least squares problem, what that means is you're solving a least squares problem, and your line exactly goes through every single data point. If that happens, which it doesn't, then you can get a faster stochastic gradient algorithm. And there's a few other cases like linearly separable classification. Okay, so that's sort of the setup. And rather than going into the technical detail, because many people are not technical, I'm going to tell you the story of how this algorithm came about and what sort of the things we were thinking about, and a lot of failures that happened along the way. A lot of failures. So it actually starts in 2005, 11 years ago. I finished my master's at University of Alberta, and we built a machine learning system for automatic brain tumor segmentation. This image takes MRIs. So we're imagining someone sitting in the scanner like this, and you're seeing the top of their head. They've got a tumor here. If you just do logistic regression SVM, something like that, with some sort of cleverly chosen features, it'll give you output like this, which is okay, but it's got holes and little points that may be hard to see. And we found that you could do better using something called a conditional random field. So now deep learning is the hottest thing in machine learning right now, but in 2005, conditional random fields were the hottest thing. These are the second most cited paper in the 2000s in the machine learning world. Now they're coming back because people have realized they're not mutually exclusive thing. You can put a conditional random field on top of your deep network. The advantage of these things is you can model dependence between labels. I can say well, I can't really have a tumor pixel in the middle of nowhere, so I can model that the sort of adjacent pixels are likely to receive the same label. So 2006, I came over to UBC to work with Kevin Murphy, and we wrote this paper on training conditional random fields with stochastic gradient. It was really slow to train them. We wrote this paper, and since they were so popular at the time, this paper got a bunch of citations. So if you look me up on Google Scholar, you'll find that my top cited paper is this one. And it's a little bit embarrassing, because if you download my code, it uses the deterministic method. So the thing that in some sense people have cited me the most for is something that I absolutely do not believe in and do not do in practice when I give people code. Why is that? It's just easier to use. Stochastic gradient, you can make it look good in your papers, you can play around a lot, but if you want something to work out of the box the first time, it's just not reliable. It's hard to pick that step size, it's hard to decide when to stop, and it goes really slowly, even if you're lucky. So I thought that we would fix this problem. So the next year, we started playing around trying to develop a better method. We didn't have much success. We got a rejected NIPS paper. That's what came out of the summer. 2008 came my PhD proposal, and I was like, we need to solve this problem. And I looked this up today. This is the first version of that graph that I showed you, though the colors are a bit different. I guess the stochastic gradient was still green. The deterministic was red at that time. And so I showed this at my thesis proposal defense, saying this is a really important problem. This will be so exciting and impactful. And my committee was not too happy with that. They're like, this is too hard, you're doing too much, focus on existing projects and so on. And I just want to put that there because I know that some of my students are around, and I kind of tell them some of these same things, and it's good to see that it happens to everybody. Okay, so I got a postdoc in France, and I was going to go there. And as some of you may know, it can take a long time to get a work visa in France. So I had this like extra 3-month limbo period where one of my committee members offered me a sort of a 3-month postdoc. And he was the one who told me I can't work on this problem. And I was like, oh, what problem do you want to work on? And he's like, oh, he didn't have an idea. And I was like, let's work on this. And so we made this red line. We made one of the obvious lines you can think of. So it was based on controlling the batch size. Instead of grabbing one random example at each iteration, on the first iteration we'll grab 1, but on the next one we'll grab 2. And then the next one we'll grab 3, the next one we might grab 5, and so on. So the number of random examples we look at slowly increases over time, and that way we transform from the green line into the blue line. When I went to my CRF problem, the one that I cared about, we got empirical results that looked much like the theory. So here the colors are exactly the same as in the plot that I wanted. Here's our deterministic method. This is something called LBFGS. It's a very fancy quasi-Newton method. For stochastic gradient, I didn't want to commit to a step size, so I just plotted the 3 best step sizes I could find. So that seems like a reasonable estimate of its performance. And then the red one was the new one. And there's a very small performance improvement. It kind of cleans up the beginning. So it follows the stochastic method, but then the slope is the same here. Whatever. That's just an extra 10 iterations. That's not a big deal. Okay, so in France, we asked this question. Can I have an algorithm that only looks at one random example on each iteration and only requires a polynomial number of iterations? I don't want to be looking at more and more examples on each iteration because that eventually just kind of gives me the same thing. I've asked this question to the audience many, many times. I'm always very heavily leading up to it. But the first time I showed a slide like this was in Edinburgh, and there was a fire alarm right at this moment. So we all went down, and people had their smokes, and there was lots of famous people there. And then we came up, and I've been leading up to this. So there is an algorithm that achieves this. It's called the stochastic average gradient, or the unfortunately acronymed SAG algorithm. Looks at one random example on each iteration, computes its gradient, then it updates its memory of this example. So this is the difference with the regular stochastic gradient. We're keeping track of something about each example. We're not just looking at random things. I look at a random thing, and then I look at what it was before. Now we update our model based on our memory of all the examples. So as in gradient descent, we're basing our update based on all the examples. It's just that the memory for all of our examples, except for the one we pick, is going to be out of date. If you want to see that as an equation, it looks like this. Now, this looks exactly like the gradient descent equation, except for I've put an IT here instead of XT. So what is that? On each iteration, we choose a random example IT. I don't know if that's the best notation. But the terms in this sum, this is the last gradient I computed for each example I. So we're imagining I have a table that has all the gradients. It has one gradient for example 1, 2, 3, all the way up to n. Each time I'm basically swapping it out. I pick a random row in that table, I get rid of the old gradient, I add in the new one, and then I use the average as my direction. So you can think of this as gradient descent with outdated gradients. Instead of updating all n of my gradients on each step, I update one gradient on each step, and then I still do the gradient descent step. Now, I'd like to say that we came up with this algorithm ourselves. Our only contribution from the algorithm side was actually saying we should pick the example randomly instead of going through in order. So if you go through in order, it's called the IAG algorithm. But actually picking randomly is incredibly important. It's what gives you that property. If you go through in order, you don't get that nice property. It actually works terribly. So here are two experiments on standard logistic regression with regularization problem. SG and ASG are two stochastic gradient methods that I've tuned the hell out of. And if you look at our paper, we actually compared to 14 other stochastic gradient methods because the reviewers just didn't believe us. We just submitted it and they said, no, you haven't compared to this. And I'm like, okay, we'll compare to that. And we submitted again, and they said, no, you haven't compared to this. And eventually we wrote, we're happy to compare to any stochastic gradient you throw at us. We'll include it in the final version. We don't believe that any of these algorithms, which we can prove take an exponential number of times, are going to outperform the new algorithm. The new algorithm's not on here yet. I haven't put it there yet. These are the deterministic methods. AFG is called Nestrov's method. LBFGS is a fancy quasi-Newton method. And you see that, well, on this data set, the deterministic methods eventually catch up and pass the stochastic methods, but it's a little bit closer in this setting. Okay, so where does the new method go? And I love doing this because, as a computer scientist, you don't often get to do this. This is a polynomial time algorithm where there was an exponential time algorithm there before. As a computer scientist, you don't get to do that very many times in your life. You either get to do that like 0 times or 1 time in your life. So let's do that again. Look at the axis here. I actually had to change the y-axis to show the new method on the plot. That was crazy. When we started doing, we just thought this was kind of a nice theoretical curiosity. We never realized it would actually work in practice. So that was a pleasant surprise. So here you see it follows the stochastic methods, but then it keeps going and keeps making progress. And it's actually the slope is better than the quasi-Newton method, which is trying to approximate the Hessian. And similar here, it goes down, and then what I used to approximate the optimal apparently wasn't low enough, so it went down here and caused me an inf value because what I was using to approximate the true solution wasn't good enough. Okay, does anyone want to make comments at this point before I go on to the one last thing? I don't know. I think this is super cool because it was.
Which error do these plots show? Is it the training error or the generalization
Oh,
error?
fantastic question. Okay, this is the training objective function. So it's the logistic loss plus the regularization. So this is what the optimizer is trying to do. If you look at the test error, it's not so dramatic. And at this time, we didn't have an explanation of how the test error on this model works. Just last year, people did start to figure out the test error analysis, and they did show that the test error converges a little bit faster, but it's not as dramatic of a difference. The other thing I'll mention is it's really easy to set the step size in this, so you can actually, in practice, drive the test error down super fast.
Can you explain the algorithm again? I couldn't really follow your explanation for this SAG algorithm. And explain what is your intuition that why this should perform better than a stochastic gradient descent?
Right.
Thank you.
Okay. So the problem with stochastic gradient descent is so when I'm far away from the solution, the stochastic gradient is really close to the gradient. It's good enough on most iterations. When I get close to the solution, all my vectors, my gradients are pointing in different directions. So my variance is very high. So if you look at the bounds for stochastic gradient, the bottleneck comes from the variance of the gradients at the solution. The problem is they have to point in all different directions to cancel out and make a minimizer. Here what we're trying to do is converge to the true gradient. And the true gradient is going to 0. So instead of making my step size go to 0, I can just use a constant step size. Now, why can I use this? As I get towards my solution, xt plus 1 and xt, they start to get close together. As I'm converging, my iterations get closer and closer together. What that means is, if one of these gradients is old, it's less of a big deal. So my iterations are getting closer and closer together. That means my outdated gradients start to look like the real gradient at my current iterate. And I actually converge to the true gradient descent iteration as t goes out to infinity. And it's a really nasty proof, but it actually all magically happens to converge at the same rate.
So did you mathematically show that your algorithm should perform better than those algorithms that you compare, or you just had empirical results?
No, the result is the theoretical result. The empirical result was like the cherry on the sundae. It's a 20-page proof. It's really nasty. But luckily, there's new algorithms that have simpler proofs. Yep. Oh, sure.
So n here, which is the history of the gradients that you're keeping, is that fixed, or are you going right back to the beginning, keeping all of them?
Okay, so I'm not summing up over time here. I'm assuming I have a finite training set. I'm actually summing over the examples. So it could actually go back to the beginning if I haven't seen an example since the beginning or something like that. So on average, I may have a data point that's sort of n log n iterations old in the worst case. Yeah.
What's the limitation on the kind of problem you can solve with this due to the assumption that you actually need to remember the outdated gradients? Like, you need to keep a whole history of the gradient to assume that decreases the class of functions that you can actually minimize.
Okay, so what is the class of functions we can minimize? So first off, we're making a convexity assumption here because that we need that for gradient descent to work. Now, the second problem is actually we're actually making very standard assumptions. So this is more directly for Yves because he'll know what I'm saying. But you need to assume the gradient of each example is Lipschitz continuous, and you need the function to be strongly convex. If you have not heard that before, those are exactly the standard assumptions you would see in 1940 to show the gradient descent has a polynomial number of iterations. So we're not doing anything fancy here. But I need to store these gradients. So if I have n examples, and say n is 1,000,000, and these gradients are each 1,000,000 variables, I'm going to run out of memory really quickly. So we published this in 2012. 2013, there was 4 papers that proposed the exact same solution to that problem. So people have now got rid of the memory with a slightly different algorithm. Yeah.
I think I've been
Whoever's mic is on.
So I've got 2 questions which are probably just the same question. The first one is, why are you choosing your data points randomly? And then the second one, is the random choice optimal, or is there a better algorithm that is theoretically possible?
Let me answer that in like 3 slides.
Oh, cool.
My question is, you have randomness here. When you developed this, were you just doing on a single machine, or did you test it in a distributed environment? And what are the challenges doing it in a distributed environment if you're trying to do distributed training?
Okay, that's a great question. And it's a question that I purposely do not think about. You know, I'm a busy academic guy. There's only so many problems you can work on. And I knew that so many other people would work on that problem, and they did. So there's a bunch of papers on like nice parallel distributed versions of this algorithm now.
Do you know off the top of your head what the issues were?
It's kind of the usual issues with parallelism. So how do you sort of trade off doing computation versus communication costs? How do you load balance and other such things?
Right.
But it's not my area of expertise at all. So I'll just plead ignorance on that one. There's some more questions.
I have a question about the alpha t. So you are using the fixed learning rate or dynamic learning rate?
That's right. So for SAG, you can use a fixed step size, which is kind of wild. So for stochastic gradient, you need the step size to go to 0 to converge, and that's what causes you all your problems. Here you can use a fixed step size because this thing converges to the true gradient, which at the minimizer is 0.
But suppose the first learning rate is 0.01, and you don't change the learning rate even the cost tend to 0. Is that correct?
Yeah, I mean, so as with all algorithms, you need to pick the learning rate well. Now, the theory works for any learning rate below a certain value. So it's not like stochastic gradient where I need to do, 1 over t, 1 over t squared, or what is it? 1 over t, 1 over t plus 1, 1 over t plus 2, and so on, something like that. Here, there's some magical number called 1 over L, and if it's smaller than that, it's going to work, any constant value. In practice, we set alpha t equals 1, and there's a certain inequality that we can check. And if this inequality is satisfied, the algorithm is going to do what we want it to do. We just check it. And if alpha is too big, we divide it by 2.
So on your plot for the cost, I mean, in a different page, and they are using the same learning rate or different learning rate. So
what's that?
Yeah, in another slide, I see them different plot. Yes.
Yeah.
Yeah, previous one.
Yeah.
So you are using the same learning rate for all curve or different.
Okay, good question. So for this algorithm, there was you only need to pick the learning rate on the first iteration. So after that, it uses a line search because it's a deterministic method. Here I plotted all 3. In this plot, to be as generous as possible to the stochastic gradient methods, I tried all the step sizes and I'm plotting the best one, picked afterwards. So stochastic gradient methods are totally cheating in this plot. For SAG, it's using a line search. It's just run once, and it adaptively finds the step size. If you change that initial step size, as long as you don't make it too small, the curve will look exactly the same, up to the location of these bumps or something like that. I don't have the plots with error bars, but if you look on archive, you can see the error bars are actually quite small.
So I realize there's not going to be a proof, but have you done any experiments on non-convex problems, and how does this perform? Because like state of the art is still using various stochastic methods, for example, in a deep network or something like that.
Okay, so I have not done that personally, but there's a new state of the art algorithm for PCA, which is a non-convex problem. And that's based on the memory-free version of this algorithm. So PCA is a non-convex problem where this algorithm has sort of made a new state of the art. In the concept of neural networks, I've heard very mixed results. So some people, nobody really says it works badly, but some people just say it works kind of as well as other things. So why would I do something different? But yeah, some of my students are playing with that, and I think there's still a lot of room for improvement in the neural network training.
With a fixed learning rate and a memory of old gradients from the beginning, why does it not overshoot the optimum?
It does overshoot the optimum, but then it comes back.
Okay, and it's just fairly quick to come back.
Yeah.
Okay, thanks.
Yeah, it definitely overshoots. There's versions of it that try to fix that. Okay. So since 2012, that was when the paper came out, there's been a whole bunch of work on the topic. So one of the most notable ones is there's a version called SVRG, which has no memory. So instead of being O of n times d, which is crazy if you have a large number of features and examples, this one is only O of n. No, sorry, O of d. You just need to store one vector the same size as your solution vector for a few more gradient evaluations. We found out that there's nothing really special about SAG. There's now like a dozen algorithms that have shown to have this exact same theoretical property. There's versions for sparse problems, constrained problems, non-smooth problems. There's quasi-Newton versions. There's accelerated versions. There's versions for certain non-convex problems like PCA. There's versions that use parallel and distributed data. So I guess I'm going through some of the questions here. And there's also analysis showing that it can improve the test error. But on the test error, it's not a phase transition. You're not going from exponential to polynomial. On the test error, you're always exponential in the number of examples. You can only improve the constants, but you can show that it does improve the constants. Beyond improving speed, as I've hinted, it also addresses some of the other annoying issues of SG. It's easier to tune the step size because as long as it's small enough, you get this nice result. And it's easier to decide when to stop. And the reason for that is that this value converges to the true gradient. And so if this value is super small, it means your true gradient is getting super small and you can't make much more progress. Your function's almost flat. If you don't trust me, try it out. If your stochastic gradient algorithm is 3 lines of code, this is 5 lines of code. You can also have the code for my webpage, which has the line search and all the fancy stuff. It's in scikit-learn. If you've seen an advertisement on the internet today that didn't come from Google, it most likely came from an algorithm or a method trained with this algorithm. So the second largest internet advertiser, they hired my co-author. They paid him a lot of money. They actually tried out the algorithm before they hired him. So they read our paper, they tried it out, they found it was fantastic, and then there was negotiations, and now he's being paid, well, much more than UBC pays. And it's also used in an academic application. So the paper has like 400 citations or something like that, the two of them. But one of the neat ones was called Building Proteins in a Day. So classically hard problem in computational biology is protein folding, and this algorithm was able to help drastically reduce the cost there. Okay, but here's the sad part. Going back to the whole problem that motivated this, the CRF problem that I wanted to solve. Ran it, compared to some state-of-the-art methods. There was my nice hybrid method. Here we've got LBFGS, stochastic gradient, AdaGrad, whatever. It works maybe a little bit better or the same. So I've wanted to solve this problem for 10 years, go off to France, prove this amazing result, fancy new algorithm. The problem that I actually care about doesn't really make a difference at all. Yeah, you shouldn't use it. Okay. But that relates to one of the questions that I said I would ask later. Maybe random sampling is too naive. So for classic stochastic gradient methods that need an exponential number of iterations, non-uniform sampling, you can prove that that's not going to solve the problem. That can improve your constants. It can't change the rate. For this algorithm, you can improve the rate. So we want to sample some training examples with higher probabilities than others. I don't want to just go to a random web page. I'm going to try and figure out which are the important web pages to go to and visit those more often. And the web pages that aren't affecting my model, I'll visit those less often. So the key idea is I want to bias my sampling towards the examples where the gradients change quickly. This is a delayed gradient method. If I have an example where the gradient changes very slowly, who cares if it's delayed? It'll still look exactly the same. If the gradient changes very quickly, I need to see that example a lot in order to have it converge quickly. So recent work by us and others showed that that actually does improve the convergence rate. And in our code, we have this kind of nice trick to estimate the importance of each example as you go. So it tries to learn which parts of your data are important to visit often, which parts are not important. Now, I stole this example from an SVM web page or something like that. If you're in this setting of linear classification, classic machine learning model that we all know and love, how fast do the examples of the non-support vectors change? If I'm doing like logistic regression or something like that. They end up changing extremely slowly. So what actually ends up happening is it's going to focus all its effort on these points and very rarely visit the points that are well classified. The algorithm automatically figures out what the hard examples in your training data are and samples those more often and starts to ignore the easy examples. And now if I go back to my CRF problem and have the non-uniform sampling, I get sort of that amazing improvement that was unexpected on the other problem and now shows up here. Okay, I'm going to wrap up. Take-home message. So this SAG algorithm, very nice theoretical result, but actually it works a little bit better than the theory predicts. So that was really nice. It's a black box stochastic gradient algorithm. It adapts to your problem difficulty. There's a line search. You know when to stop. It hasn't completely fixed all the annoying issues with stochastic gradient, but I think this is really nice because I don't have any stochastic gradient codes on my webpage, but I have this code on my webpage, and if you download it, I'm pretty sure it'll work. Led to a whole bunch of other algorithms and applications. And finally, I want to say that if you are looking for employees or you're looking for an employer, I've done a lot of one-to-one matching over the past few years. I'm trying to avoid that. So some students set up a data science job board. So if you're looking for employers or employees, make a profile there. I have 183 students taking my class this term. I'm going to encourage all of them to sign up. So if you're really looking desperately for machine learning people, there may be 183 of them coming on the job market in December or April. And finally, thank you so much for the invitation. Thanks for coming out, and I'm happy to answer any more questions and have discussions and so on. Yves?
Can you elaborate a little bit more on line searching and when to stop termination?
Okay, so let's just do this live. So I need alpha t to be less than or equal to 1 over L. Cool. So L is a measure of how fast the gradient can change. So it's sort of a bound on the eigenvalues of the Hessian. That seems really annoying to compute, but it's just for one training example. It's not over the whole data set. So what I could do is I could do something like, I could just test gradient Fi of, oh, thank you, surface. It didn't look like my, my collar touching it. Y less than or equal to L, X minus Y. That's the inequality that L has to satisfy. If I have an estimate for L, I can just test the inequality at the random example I pick. If my L is too small, this inequality violates it, I just double it. That's it. I stole it from the Russian guys from the 70s. I have no proof that that works. A guy in Japan told me that for his problem, my trick didn't work, but then we found a minor tweak that made it work. Pardon? Oh, when to stop. Okay, so this thing, sum I equals 1 to n, gradient Fi of xit, that converges quickly to the true gradient, xt. So normally when we implement gradient descent, we test the size of the true gradient to decide when to stop. Now I've got this estimator that's converging at the same speed that my algorithm converges to this quantity. So I'll test the norm of this quantity, which I know, as an approximation of this quantity, which I don't know. Something you completely cannot do with stochastic gradient, because stochastic gradient, you don't have this global view of the function. Yeah?
There was a question earlier about using SAG and neural network architectures. I actually missed the answer to that. Could you repeat it?
Mixed, not super exciting results, I would say is the summary.
Okay.
Hello. You went with your CRF problem. You went back to non-uniform sampling and found the improvement. Did you try that again on the logistic regression with regularization? Did it make more improvements?
Yeah. So I normally show that plot. I didn't today, but so in our original paper we showed results on 9 data sets. Now, you'd think I would have cherry-picked those 2 examples that are so dramatic, but 7 out of the 9 data sets had that dramatic effect. 2 of the data sets, SAG was just basically along state of the art. Once we did the non-uniform sampling, it made those 2 data sets look dramatic too. And the other data sets, it didn't really make a big difference.
The non-uniform sampling seems to work for particular problem sets. That's where it makes a difference?
Yeah, exactly.
And what of those 2 data sets do you think it was that the non-uniform sampling made the impact? Is there something that you could pin it to? Like what sort of data sets or problem sets that non-uniform sampling works well with?
I would have to think about that. I don't know the answer to that.
Perhaps lots of irrelevant data points that aren't particularly informative. Yeah, makes sense.
Yeah, that would definitely make sense. So it certainly learns to ignore, or at least sample them not very often, the very well classified data points. For CRFs, you don't quite have the same picture of support vectors. It's a bit more complicated.
I'll update the question then.
Yeah.
So is that the optimal form of non-uniform sampling? Or is there a lot of potential for future improvement?
Yeah, great question. Under certain assumptions, the one here is optimal, but those assumptions are a little bit brittle. in that if I start doing like Newton-like versions or accelerated versions, it's not clear that the same thing will still be optimal. So I have a student working on this now, trying to find out if there is a better thing. It's not clear that there is or not.
And those assumptions are not about your data set, they're about what particular, so you mentioned
they're not
applies
about
to Newton-like methods.
Yeah, so the non-uniform sampling is sort of, there's a consistent way to do it that it doesn't matter what your data is. So you use the same strategy for every data set.
Hi, thanks for your contribution to science.
I don't think I've ever heard that before. Thank you. You made my day.
So I'm not a researcher, I'm a developer. And between working on your features or collecting more data or working on novel training algorithms, where do you think a business would be able to get the most value from, say, maybe one of your graduates who you are saying is entering the job market, or from some other junior machine learning resource?
Okay. Yeah, great question. I'm going to try and take a two-faced view on that question. So the first is, if I just want to make my model work better, should I work on making a better optimization algorithm? Should I work on better features, or should I get more data? You almost always pick features in that case. Features can do a lot. Having the right features makes a world of difference. Then you pick data, then you pick algorithm. Now, in terms of hiring one of my students, they don't know what your problem is, so they may not be as useful at picking features as you are. So they're probably more useful in terms of developing algorithms or so on. The other things they can do is if you don't quite fit in the standard supervised learning framework, those are the things my students are a bit more useful at. If for some reason you can't just fit into this simple cat-dog thing, then they're a bit more useful if you need to do some sort of feature creation or something like that.
Hello? Oh, hi.
Hey.
Can memoryless seg be applied to streaming data?
So there is a paper called Streaming SVRG. It was written by a bunch of guys from MIT last year. What they showed is that, it's a very complicated paper and complicated to even explain what they were doing. But basically they showed that if you ran Streaming SVRG, you did well with the same constants as if you exactly solved the optimization problem for every value of n as data came in. So if I ran Streaming SVRG on 1,000 data points, I would do as well on test error as if I had exactly optimized my training error on those 1,000 data points. So that sounds kind of cool, but there's a little thing hidden there because you can overfit if you exactly optimize the training error on 1,000. So so streaming SVRG is definitely a thing. There's this sort of fascinating theoretical result, but it's I don't think anyone's actually using it yet. There's several NIPS papers on it this year, I noticed, including one by Mike Jordan, who's the serious machine learning guy. Okay, maybe we should stop there. Okay, thanks everyone for coming out.